Good morning, all. So today we are going to have a wonderful lecture session in the topic Advanced Tools to Study Material Properties, which will be delivered by Dr. P.A. Praveen. He is a postdoctoral fellow, Department of Physics, Indian Institute of Science Education and Research, Tirupati. And he completed his doctoral degrees in 2019 from School of Physics, Bharatdasan University. And his research interests are organic semiconductor synthesis and fabrication of microstructure, photonic devices, fabrication and measurement, computational material science, modeling, structural properties. He authorized 3 books: Semi-Empirical Modeling and Experimental Evaluation of benzimidazole, Metal Organic Complex for Nonlinear Optical Applications, Springer Gravitational Waves Explained. So with this brief introduction, I invite Dr. P.A. Praveen to deliver his lecture.
Thank you, sir. So, good afternoon, all. Once again, I thank Jamal Mahmood College as well as the staffs of Department PG Department of Physics for their organizing such a great event. Especially, I thankful to Ishak sir for inviting me to this event. So today we are gonna see advanced tools on the topic advanced tools for material science. As far as I understand, I have seen a mixed audience in this webinar so far. Even though there were many undergraduate students, there were postgraduate students as well as some research scholars and even staffs are attending. I keep seeing this mixed audience. So I prepared my talk accordingly to this. Considering undergraduate students most often or most of the students don't study material science in particular in their curricula, but they are studying the part of the material science in different aspects, which we will see later. So in case if you want this slide deck which I'm going to present, you can download this slide deck from this link, or sometimes I included commands of certain programs in this slide deck too. So in case if it is not visible in your screen, you can go to this link and you can view the slide deck live in your device. So with these points, I wish to let's see the outline of the talk. So as I mentioned, since many people, if we consider the undergraduate students, they might be new to the field of material science. So I'm going to briefly discuss what is material science. And considering material science, it can be studied by using both the physical as well as both the experimental as well as theoretical way. So, since it is theoretically oriented, and the tools that we are going to see are mostly simulation tools, so we just see some of the physical theories. Very briefly, I'm going to discuss. Then today I'm going to discuss two theories. One is density functional theory, which is the widely used method today in material science to simulate a lot of materials properties. And another one is semi-empirical analysis. Even though it has been not used by many people, which is older than DFT, but it's not that much used by people because due to its accuracy limitations. Nowadays, it has been widely used by many people and it's giving very good results. Today we are going to see these two methods and the tools relevant to this two things. So first, let's see what is material science. Um, so it is a command aspect of like you could see it combines solid state or condensed matter physics. If you are considering the properties, it has electronics, optics, magnetics, thermodynamics. These people are these subjects we have been studied explicitly in our undergraduate, sometimes even in our postgraduate studies. But these are the combination of certain single field, that is material science, and so often physics can be considered as light matter interaction. So material science is studying these interactions, and it has roots to chemistry, and it branches up to biology. So it combines entire scientific field, and it has potential applications of almost all the devices, or whatever be the thing you are using, that is made up of a material, and it has certain properties. So we can say material science entirely contributes to the all humanity. So, considering material science as a scientific field, it can be either considered as a tetrahedron, or in more modern terms, we can say it as a material science triangle. In material science, tetrahedron, these are just symbolic representations, like what are the futures it has, and how we are going to approach these things. Are the main aim of providing such a structures. This tetrahedron are classical one, and people used some decades ago. So with the introduction of nanostructures and nanomaterials, it has been slightly reduced, and with the invention of new and multifunctional materials, it has been usually nowadays it has been depicted as a material science triangle instead of a tetrahedron. So in a classical way, we will have a structure, or we will first find a structure. Then, based on the structure, we will study the properties. We could call it as a structure property relationship. Then we will process the material, so to find its suitable performance, because depending upon the processing techniques, as well as manufacturing methods, the performance of a material can be altered. But these are not independent fields. So depending upon the structure, the processing may vary, and depending upon the processing method, the properties may vary. The depending upon the property, the performance may vary. So these are all interconnected, and we have to optimize these things to get a final product, or a better product. In modern terms, we have been looking for functional systems. So initially, we would have a initial individual material components. We would, by utilizing experiments and theory, we would devise functional systems. Then, by interface design, we could optimize these systems, and this can be extracted to the application level. So these both are all same, but at the outset, it can be said all the structure properties of materials have been related. By suitably tuning the structure, the properties can be varied. So the question is how a structure can be studied, and how the properties can be characterized for a particular material. So which we are going to see in this slide. So this can be done by both the ways. As I said, it can be done with both experiments as well as using theory. Um, Considering experiments, usually we would use X-ray diffraction to study the crystalline structure, and spectroscopic methods like FTR, Raman, to study the molecular structure, and methods like atomic force microscopy, scanning electron microscopy, such things to study the surface or nano level properties of materials. And depending upon the applications, if you want to study the mobility of a particular compound, you could go for some like IV characteristic, as well as if you want to study the emission properties, you could go for photoluminescence of the particular material. So depending upon our requirement, we can use different methods, different experimental techniques to um, study the properties of materials. On the other hand, these methods are often very expensive, and in order to optimize a material, we have to do lot of experiments, and lot of characterization is literally impossible. So in such a case, theoretical analysis very handy. Theoretical analysis comes very handy, and we can simulate almost all the properties by using suitable theoretical models. Since most of the material properties are arise due to valence electron, by properly studying the valence electron, we could exactly simulate the material properties which we derive from the experimental things. So as you know, almost all of you know, these material properties, these electronic properties can be studied using Schrodinger's equation, but there is no direct way to solve the Schrodinger equation. So you people, if there is some postgraduate or research scholars here, you may have done solving analytically Schrodinger's equation for hydrogen atom. But when we move on to the next level, even for helium, it is very complicated to solve the Schrodinger's equation. There could be multi interactions, and usually it is very hard to solve such a thing. So what we do is often we apply some numerical solutions to solve the equation, and based on that numerical solution, we would get the wave function properties which can be directly correlated to the valence electrons. And once you know the electronic properties, that could be extracted or extrapolated to the mm, materials properties or the properties of a particular molecule or atom. So there are many numerical methods have been developed over these years. So this is an almost 100 years old problem. So there are lot of techniques are there, and there were many successful methods there. So that there were many commercialized and open source solutions are available, like Hartree-Fock method, density functional theory, and semiempirical methods are used to solve this Schrodinger's equation, of which Hartree-Fock is often of Hartree-Fock or something called molar cassette or coupled cluster methods. These are called Ebbinghaus methods. So they solve the system from as it is, and exactly provide you the solution. Whereas in the case of density functional theory, you often consider the density of the system, and you calculate the functional of that particular system. Whereas in the case of semi-empirical methods, you often what you are doing is by substituting some random experimental as well as theoretical values to the semi-empirical method, you could fasten up the calculation and get some suitable results in a very less computational cost. So what we are going to see today, so we would do geometry optimization of a very simple system like methane, and we could simulate a FTR, Raman, UV visible absorption spectrum, as well as fluorescence simulation using this using density function theory, as well as we will do geometry optimization and nonlinear optical properties of zinc oxide nanoclusters. So for DFT analysis, I'm going to use a package called ORCA, and for semi-empirical, I'm going to use a package called MOPAC, which we will see in the next slides. So, but before that, I wish to stretch one point, what is called geometry optimization, because if there is some undergraduate students here, they might have wondered, so they could imagine what is FPR or what is Raman, something like that. That could be material property, but they would slightly wondered what is geometry optimization, because usually in computational material science, we often design a molecule by using some chemical drawing, structure drawing software, or we could get the structure from single crystal XRT. In both the cases, the energy of the system could be slightly higher, or it couldn't be uh, have the proper structure, because usually the chemical system is very stable at its lowest energy. So that lowest energy is often called global minima, and the ultimate aim of the geometry optimization is to obtain the global minima. But this is usually not possible, because that could be this kind of valley peak structure. So that usually sometimes we struck up with local minima like things. So geometry optimization is very important. In case if we didn't optimize the geometry properly, the entire system's property may vary. So so I don't want to discuss these details, and so I just want to discuss these things in very briefly. In case if you want to see this one, you can check this link, or you just can Google it. So there are a lot of discussions available in the internet. So what happens when you optimize a molecule? So the system arrange the atoms and atoms and its positions by suitable or different possible ways. So it will reduce the bond length, it will increase it, it will adjust its bond angles, so that it will try by adjusting these things, eventually it will study the energy variation with respect to this modification. So at a particular point, the energy of the system is really low. It should be um, considered as the global minima of the particular molecule. Okay, so let's move on to the demo version. Sorry, let's move on to the demo of some simulations. So we require following packages for these simulations. We need a Marvin sketch for drawing the molecule, and in case so I'm gonna use Avogadro for now, but I will show you how these Marvin sketch can be used for trying chemical structures. Because yesterday you have sort of Sabaratnam discussed a lot of scientific drawing programs to use in your academic manuscripts. As well, you could add this chemical drawing software to that list too. Then we use we can port the corresponding molecules to Avogadro or Gabbard to prepare the input files. So first, let me to start the Marvel sketch. Probably, if there are some chemists here, you might have known ChemDraw as well as ChemSketch. Those who are commercial packages available. Marvin Sketch is also a commercial package, but it has been distributed free for academic usage. I personally feel very useful, and it's a very nice program comparing to Canberra. It's my personal opinion, but that depends on you. Let's see. Okay, it's loading. Yeah, so like usually this is how chemical editor looks. So there could be default some structures. You could choose some atoms from here. Here's the periodic table. In case if it is not available in the shortcuts, you can use any material from here. So here I'm going to draw, okay, let's draw anthracene. So if you so usually these are all, as I said, when you draw a molecule like this, it is not optimized because we don't know the exact bond length or bond angles. So you can clean the structure using the inbuilt things, or otherwise you can export it to. So we can save it as saying as anthracene. Now I'm just closing this, and if you see the file have been saved here, you can it's a text file only. The molecular format is this is the Cartesian coordinates of the different systems. If you see, the hydrogens have been not added to the system. When you exactly using this system for simulation purpose, often you encountered with the error. So one best way is you could visualize these things, these molecular files before using this for the computational simulation. Also, you may require some GUI programs to get to prepare the input file formation for the molecules. So I'm using one program called Avogadro. This is an open source program, and it's a very nice and very useful program considering for computational material science. So now I'm you opening our saved molecule. So since hydrogens are not here, I add the hydrogens explicitly, and you could do some pre-optimization, like molecular. There are certain methods, simple methods called molecular mechanics that is based on Newtonian theory. One such a method is UFO, which is called, which can be abbreviated as universal force field theory, which could be applied to almost all the atoms in the periodic table. So you may use that one to pre-optimize the system. If you could see, the system have been optimized. So in such a way, a molecule have been pre-optimized, and this can be used as the used for the input file preparation. Um, so here, what I'm going to do is initially, if we take these kind of molecules for a demonstration purpose, it would consume a lot of time. So I'm gonna use let's see very simple molecules like methane, so that just a moment. So let's create a very simple molecule like methane. So we are gonna do optimization for this one, and we will do spectral simulations for this one. Okay. So initially, let's do So I'm setting up the force field. Again, the force field is universal force field theory. You could choose a number of steps depending on in more the number of steps. Better could be the optimization, and lesser the convergence, better could be the optimization. So um, okay, this has been optimized. What I'm going to do is I'm going to save this as in the folder JMC. I'm saving this molecule as methane. Now let's close this one.
Sir, voice கொஞ்சம் low-ஆ இருக்குங்க sir.
Okay, I will adjust. Sorry.
Yes, sir.
So now we just gone to this folder, and you could see that corresponding input file here. So this is the way to prepare molecular input file for any computational calculation. You similarly for whether if you are using Gaussian or a Dalton, even Amsterdam ADF, Amsterdam density functional package, whatever be the thing, this is the basic way to prepare the input file. Now let's see the some of the commands to which could be used for geometry optimization for ORCA. So I'm just simply copying these commands, and I'm renaming this as methane.inp. So usually for ORCA, the input file name should be n with .inp. The extension should be .inp. So I'm using a methane inp. Here, for optimization purpose, I'm using the keyword OPT, and I request a type SCF, and I use the functional B3LYP, and there are two kinds of B3LYP functional available in ORCA. So if you are about to compare your results with the Gaussian results, it is better or advisable to use B3LYP/G. And as usual, for B3LYP 631 G basis set is widely used, so I just simply adopt it. But depending upon your problem, you can use a different basis set. Since I'm going to use the optimized geometry for fluorescence spectra calculation, I need Hessian. So I request Hessian during this geometry optimization, and I request in the output I request all the detailed molecular information has to be printed. Printed. This XYZ file mentions the input coordinate should be read from a file called methane.xyz. So that's it. We can simply close it now. We can run it by orca methane.inp, and we direct this output to methane.out. So it would take a few seconds to complete. So usually it is better to run these kind of jobs in a server or in uh, better machine, because depending on when the size of the molecule increase, the computational calculations time is usually increases, and you can paralyze the thing in the server. Okay, the calculations have been finished. You could see now if you open the data xyz file, it has been changed and it has been modified to the optimized version. Optimized version, as we discussed, as we seen, this is the lowest energy form of that molecule. Then the Hessian have been created and other properties have been here, which we will see if possible, if time permits, we could see what is the use of other things. But here our aim is to create the FPR spectrum. I'm going to create a new input file for the FTR simulation. So I create a new input file and renaming it to far.inp. So here I'm going to use methane, so which is the optimized output. Here too, here you could see I have removed the keyword opt from here because since we have already optimized the system, I have removed that keyword from here. Also, you can request a frequency calculations during even during the optimization. So in a single file, once it's finished the optimization, you could request vibrational that is the FTR's spectrum simulation, which could be used as an estimation how potential or how qualitative is your optimization, because if there is some negative frequency in the system, we can say the system is not optimized properly. So that it is suggested and it is always better to do a frequency calculations with optimization. But here we are going to run the calculation alone for better understanding. So I have included these keywords, and now again ORCA FTIR. Now the input file is FTIR, so I name it here, and I direct it to FTIR.out. Let's wait for a few minutes. For visualization of uh, these computational materials in output, we use a program called GabEdit. So usually, if you are using Gaussian or SCF density Armstrong density functional package, you would have provided with the default GUI package with your commercial package. But in the case of ORCA, there is no commercial GUI or official GUIs available. But packages like Avogadro and Gabadit can be used for this purpose. And Gabadit is a very powerful tool to view process your computational results. Now our FTR spectrum calculations have been done. I'm gonna to visualize this spectrum. So I'm using GabEdit package, and in tools I'm going to visualize by choosing read frequencies and intensities from ORCA output file. So GMC FTR. So if you see the corresponding peaks have been visible here. So in case if you know the experimental values or previous values, you could compare and see the things. Also, one more thing you can do is you could visualize the corresponding vibrations, which I'm going to done using FTR spectrum. Sorry, using Avogadro. Um, just a moment. So in the meanwhile, before that, we will create an input file for the Raman simulation, and we will run that one, and we could see that vibrational things in the meanwhile while the calculation is running. So this is the input file for Raman calculations. So now I'm naming it to raman.inp, and yes, the input file. So if you see here too, I'm requesting the frequency calculation, but now this time I'm requesting a numerical frequency and going to calculate the polarizability in the system, so that which could be used for the simulation of Raman frequencies. So here too, we have to change the input file name to methane.xyz, and I'm running the calculation by giving the command dot input Raman dot out. Okay, while it's running, we will see the output of the FTR simulation which we have done earlier. Documents, change. So if you see here the list of um, frequencies are vibrational frequencies are available here, and if you choose the particular frequency and start animation, so you could see like this. Maybe if you have take a course on atomic and molecular physics, you might have studied like bending, vibration, something like that. Bending, mapping. So there are many things that you could do. So similarly, for some other so it is. I hope it is visible to the screen. So in this way, the exact nature and what are the components in the molecule contributing to the vibrational spectrum or vibrational absorption of the system can be understand using these simulations. So yeah, it's still running. So I have already done this calculation for the example purpose. So once the calculation finished, you will get the output as like that of the previous one. Here in this case, what are you going to do is you are going to visualize the Raman spectrum instead of the IR spectrum, and choose the read frequencies and intensities from ORCA output file. And as I told you, I have already simulated this one. Use Raman, and these are the corresponding peaks. If you could see, there were additional peaks than that of the usual vibrational frequencies. Here too, you could visualize the corresponding molecular interaction in the same way as it for the FTR spectrum. But for time's sake, I'm just simply skipping this, and Moving the next one. Okay. So for UV, we need these inputs. So I'm just simply copying this, create a new file, as renaming it as uv.input, and substituting the input file, and renaming it to methane. Note that here we need the Hessians, which we have calculated during the geometry optimization. So I am substituting the name methane, which we have done already, and I chose the number of roots as 5. Since it is for only for demonstration purpose, I choose 5. But in the actual cases, you have to choose more number of roots for better quality. So again, here too I choose B3LYP and the same basis set, but I have included RIJ and the grid for fast calculate to calculate the things a bit fast than the previous one. Since we are gonna ask for the TDFT calculations, usually time dependent calculations consume much time than that of the normal calculations. So this kind of fixing grid and adjusting the things are necessary to speed up the calculations. So I'm saving this one, and I'm running it by the same keyword, uv.input to uv.out. So it would take actually what I would do is it would create a new input file, which we call it as a ASA input, and in the ASA input we have to request to simulate the fluorescence and absorption spectra. So let's wait for the creation of a ASA input file. So usually it would like so if you see, so once that UV calculations have been done, it would create a file called uv.asa.inp. And if you open this file, it would have a series of inputs. So usually this would have 5,000. We have to, in case if you need up to, these are in centimeter inverse one range, you simply have to convert this to nanometer and change the values corresponding to your requirements. So usually I want, since we are having a organic molecule and usually it will have a strong absorption in the UV region, I request absorption range from 2000 centimeter inverse to 10,000 centimeter inverse for both absorption and fluorescence. And the number of points, higher the number of points, better would be the continuity of the spectrum. So I here I request 1024. And one important thing is, in order to calculate the Raman spectrum, since these spectrum is going to be vibrationally resolved spectrum, we need a Raman order of 1. So all other things we don't need to change and keep it as it is. And again, so here I'm canceling this job. So if you for running this ASA input, you have to calculate a separate program called ORCA.asa. So instead of just putting ORCA, you have to call it as a ORCA ASA, and uv.asa.input to input. Just you don't need to give any output file name. By running this, you will be provided with you will be simulated with two new output files. So one is fluorescence data, and another one is absorption data. Since it would consume a bit time, even though it is methane and it's a very small molecule, so it would consume some few minutes, 2 to 3 minutes. So I just simply showing this one, and we could see the corresponding spectrum of the uh, simulated output. So here, since this has been given as .dat file, this cannot be directly open using the gap edit. So what we have to do is in the UV spectrum, we have to choose read energies and intensities from an ASCII file. So it is in XY format, and we have to choose. I choose all. The first one is absorption, or one thing you can do is so this is the uh, spectrum. What you can do is instead of going to gab edit, since these are dot data files, you could directly plot using a plotting software. So here, let me to show you plot uv.asa dot absorption dot data. So you could visualize the corresponding absorption spectra here. You may see this is the UV region. Since it is the centimeter inverse one, we have to, if we increase the mm, uh, number of, increase the range in the ASI input file, we could visualize the exact peak in the UV spectrum. So in the case of fluorescence, instead of absorption, I change it to fluorescence. You could see the spectrum has been slightly redshifted, and you could exactly see the fluorescence peak here. Since it is vibrationally resolved, you can exactly see the vibrationally resolved peaks here. So so this is the case for fluorescence simulations, and let's move on to the semiempirical calculations. Semiempirical calculations are usually offer two things. One is it offers a very fast and convenient way to do the calculations, because usually for a DFT calculations you require a server or a very good machine to do the calculations. On the other hand, semi-empirical calculations can be done with even a very ordinary system, and it could produce considerable results. These results are often comparable with that of the DFT calculations, since the modern semi-empirical methods are highly developed and very properly optimized. So the results are very useful. On the other hand, sometimes it would offer lot of issues. So usually we have to, considering symmetrical calculation, one thing we have to do is to do the benchmarking of the calculations. So you have to choose a similar kind of system which have been previously reported, and you have to optimize the things for that system. By that way, you could optimize the particular program or a particular method for whether it is suitable for your calculations or not. In such a way, you could optimize that one. Then you can use that one for your actual calculations. So another advantage is it supports almost all the elements in the periodic table. If you consider lanthanides or transition metals, it is very hard to. Usually, you could observe a lot of errors during the optimization of lanthanide or transition metal complex in DFT calculations. But these things are very casual, and it would consume very less time in the case of memory calculation. And especially, there is a package called RM1 with Sparkle. These calculations are very excellent, and they provide very good results in the case of lanthanide materials. So if you are considering calculations for transition metal ions or lanthanides, I could recommend you semiempirical calculations. So here too, we are going to use Avogadro for preparing the molecule and using MOPAC, which is a semiempirical package, to optimize and do the polar stability calculation. So input file, we will optimize the geometry. Then we would verify the geometry. As I told you earlier, we need to do force calculation to ensure that we have obtained the true energy minima. Then we will do the polar stability calculations. So usually it is hard to do the nonlinear optical calculations with the TFT. You have to ask, you have to request the TDFT calculations, and it would consume much time to finish. On the other hand, using semi-empirical calculations, you could usually do the calculations within few minutes, and you could estimate the trends over a series of molecules. So that's why I have chosen semi-empirical calculations for a polar to demonstrate a nonlinear optical properties calculation. Um, for this one, I have I'm going to use a zinc oxide nanocluster. So usually, nanoclusters are have different point groups, and their energy varies with respect to different geometry, molecular symmetry. So here I'm gonna use a D2H symmetry, and we will see its nonlinear optical properties. So you, by comparing these, if you take series of nanoclusters and be comparing the results, you could say which kind of nanocluster is potential and which one you could be considered for experimental consideration. So here I'm going to use zinc. So since it is not available as a default, I use it from here. Then I will choose oxygen. As a usual thing, I will pre-optimize the things by using universal force field theory. So that's it. If you can visually see the molecule have been changed, and now I'm saving. So it has few extension. You could directly extract the input file from here itself. So I'm choosing MOPAC and generate the MOPAC input from here. So I create a new folder for better understanding. MC2. So I name it as EZNO, and I'm closing the things. Now, now let's move on to the actual folder, and if you see, you could see the corresponding command line. Here, this is the first line is the command line. Here you have to substitute the, you could request what the program have to do. So Ax means it will produce auxiliary files, or large means it would create an entire calculation details. Charge is the system's charge, and we requesting it for singlet, since it is not a triplet one. We mention it as a triplet. And there are many semi-empirical methods, PM3, PM6, PM7, RM1, AM1, like that. There are many semi-empirical methods available. The recent one is PM7. So in case for most of the calculations, PM6 and PM7 is enough. Here I'm going to use PM7. So what I'm going to do is, first I'm asking the system for charges. So by entering the keyword charges, I'm going to study the charge of the system. So I'm substituting it by, I'm running the calculations by typing MOPAC znvo.mop, and it has created the output file. If you see, the computer charge on the system is -2. So what we have to do is, when we give the actual input, we have to substitute the actual charge of the system in the case of charge. So here I'm substituting as -2, and genome is the how good the system has to be optimized. Usually, lower the genome value, better would be the geometry optimization. For bigger systems and for lanthanide kind of lanthanide or transitional metal complexes, you could choose even more bigger values, some 5 or 10 you could choose. But please note that bigger the value, lower would be the quality of the geometry optimization. So now I'm running this one. So the output, you could see the, you could observe how fast it have been done the calculations. Just by substituting the things, it would produce the output. So it has created an ARC file. So this is the optimized. Here you could see the optimized geometry here. So now we have optimized the zinc oxide cluster. What we have to do is, we have to verify the quality of this structure. For that, we have to do a vibrational calculations or a force calculation in MOPAC terms. This is nothing but the FTR spectroscopy which we have done in the DFT. So I'm simply replacing this with these keywords. So I'm removing that genome and genome, which requests geometry optimization. Here I put force to request the vibrational frequency calculation. Now I'm going to run as arc. Instead of .mop, I'm going to run arc. So it has been entered. So even by opening that file, you can see the corresponding frequencies here. Or by using Avogadro, just a moment. Yeah. So it is taking a bit longer. I think so. Yeah. So using Avogadro, you could visualize the spectrum, and you can see whether is there any negative frequency, so that you have to optimize the things further. So you may see it has been optimized properly. There is no change in the structure of the particular system, and it shows all positive vibrational frequencies. And in case if you need, you could visualize these things as we seen in that DFT calculations. So I'm closing. Now I'm going to do the polar stability calculation. So I'm going to simply change the keyword in that auth file. So instead of force, I'm just substituting the keyword polar. This would request polar stability calculations. Polar stability and hyperpolar stability calculations will be done. Since this is for demonstration purpose, I didn't include any other keywords, but usually you could request, since there are a lot of nonlinear optical properties. There is second harmonic generation, third harmonic generation, Kerr effect. There are a lot of nonlinear optical properties. You could visit MOPAC's manual to see what are the possibilities and what are the available options, so that you could request your corresponding calculation. So if you see, you have to go through your output file. You could see calculation of static field quantities, in which it has shown alpha, which is the linear collapsibility of the molecule. Then, without any request, this is the package would simulate second harmonic generation of the molecule, which is termed as the average beta. It has been given here, and for third harmonic generation, it would be, the values would be something like that. Also, these are all for static values. So at zero point 0.0 electron volts, in case if there is an incident frequency of wavelength, something like that. So the alpha and beta values vary. You can request for a particular wavelength too by mentioning E equal to something. In that input file, you could request the alpha, beta, gamma values for a particular wavelength and particular nonlinear optical property. So this has been generated up to 0.5 electron volts, which is nothing but 2500 nanometer, which is in the far IR region. You can say this kind of if it has some good beta and gamma values, it could be considered for telecommunication kind of applications. So that's all I think. So one more thing you can do with this, I'm going to shortly describe that. So I missed that one during that previous one. You could visualize the HOMO LUMO from the optimized geometry. So usually, depending upon the HOMO and LUMO, the conductivity of the system varies. So for that, I open gap edit, and I'm choosing orbitals. Documents. So these are the available HOMO and LUMO orbitals in the molecule. I choose the HOMO. So the one with 1.00 is the HOMO, and then one next to this one is called LUMO. So I'm just going to visualize the HOMO here. So I'm giving more the number of points, better would be the figure. I choose 0.01 as the ISO value. Okay, so this is the simulated HOMO and LUMO for the methane system. So you could see how beautifully it has been generated. So by taking the difference between HOMO and LUMO, you could calculate the energy gap, and you can compare this with the mm, absorption spectra. So there are a lot of in-depth structural event fields are there. So since this is those things are out of scope of this talk, I am simply finishing the things here itself. So these are the some references if you wish to go through the things. There is a book called Computational Material Science by June Lee, which offers in-depth analysis of different material science programs relevant to the field. And in case if you want to be expressed in computational material science, there were three possible ways. One is you could collaborate with some experts. So usually this is hard because everyone is busy with their part of work. So another thing is you can learn it by yourself. It would take a lot of time, and surely it would have a learning curve. And the third one is you can go for paid options. So there are something like so this one, this comets people offer a paid version of these computational material science things, and several other, I think, Coursera, and even in ThinkFic, I think there were some courses are available. So in case if you don't have much time to put forth effort to learn the things, you can look into these things. But I could personally suggest try yourself and learn yourself, so that you could develop your own way to do the simulations. And for Avogadro, to download Avogadro or Gabadit or ORCA or even MOPAC, you can follow these links. Avogadro and Gabadit are available as it is. You can simply download and use it is. And in the case of ORCA, you require an you need to download and define the path in your machine, whether it's Windows or Linux or even Mac. You have to define the path. It's a bit tricky, but it's easy. You can do that by yourself. For MOPAC, you require an academic license, so you have to apply through online, and they will provide you the license within 20 to 48 hours. But it is free, and it's not open source, but it is free for academic use. So that's all from me today here. Thank you. Hello, sir. Hello.
Sir, 1 minute, sir. He will come and join, sir.
Okay.
Hello.
Hello, sir.
Yes. Thank you, Dr. Praveen, for your efforts and painstaking explanation on various types of software used for drawing. On behalf of PG and Research Department of Physics, I would like to convey my warmest gratitude to you. Further, I would like to thank all the participants who have come here to this meeting and have got benefited from it. Thank you. We'll meet you once again tomorrow. Thank you.
Thank you. Thank you, sir.